Welcome. This is the first meeting for the modeling team for the new year and the first meeting under the new 5-year U.S. Federal Arctic Research Plan. So I wanted to say a few words about that. The accompanying 2-year implementation plan details specific objectives, which are probably more familiar to us in the modeling team, the performance elements that we had before. The new U.S. federal plan has 4 priority areas. They are community resilience and health, Arctic system interactions, sustainable economies and livelihoods, and risk management and hazard mitigations. So there are new IARPIC teams associated with each of these priority areas and other aspects of the plan, which you may explore. You may explore these other teams. I don't think the goal is to have more IARPIC meetings. The purpose of these teams is to shepherd these objectives. So the teams of the previous plan are now known as communities of practice. We're now supposed to be called the modelers community of practice. You can still call us the modeling team, which our team kind of serves as an intermediary between the research communities and the plan objectives. So if you have any other questions, there's a lot of material on the IARPIC website about the new plan and what the objectives are. But for now, let's talk about sea ice prediction, which is the topic of our meeting. Statistical models, as I wrote, distill a prediction of sea ice cover by utilizing the historical record and drawing on relations between the evolving sea ice cover and other variables. Statistical models may offer lessons for Earth system model development. So our first presenter was actually a volunteer, which you can do if you would like to present your research. You can contact either Renew or Wilbert Wire or myself or a member of the IARPIC Secretariat if you'd like to present your research. But Jia Wang is our first speaker. He is a research scientist and physical oceanographer with the NOAA Great Lakes Environmental Research Laboratory. And his title of his talk is Hindcast of Arctic September Sea Ice Cover Using Teleconnection Indices. Jia, would you like to share your screen? Okay, we can see it.
Okay. Okay.
Okay.
Good afternoon, everyone. Today I'm going to talk about statistical hindcast. And however, we have potential to use this hindcast model to do the seasonal projection. And this project is based on our data analysis by Thai, and then I have 2 summer intern and let them to train the model using our data. And so, of course, numerical model is one part, like Wieslow and many other. We also do the 5 days forecast in the Arctic as well. So the key words here is we only use teleconnection pattern indices to do the projection, to do the hindcast. The contents of motivation, and then number 2, I will show you the data we analyzed over the last 150 years. Look at the Arctic amplification, teleconnection, and ice ocean albedo feedback. And based on the finding in 2, and then we developed the hindcast model for Arctic summer, a 3 months average, and then September, because September is a single month and we are really interested in, and then summarize the results. And as we know, these are summer September ice cover from ice extent from 1979 to up to last year. And so the decreasing Arctic sea ice is due to, of course, warming. What warming is it? And we have to distinguish. And so our motivation and then objective is using, first we use 3 months average summer indices. And then I found this, we found this is difficult to do the projection because you have to do the summer average. So we use the monthly teleconnection pattern. And so to project September minimum sea ice extent. The data, the basic keywords here is Arctic amplification, teleconnection, and ice albedo feedback. This is the key to accelerate the melting in the summer sea ice. And we divide the Arctic region into 6 regions, 1, 2, 3, 4, 5. In the figure there, and 7 is the whole Arctic. We add them together to do the same. And as we know, teleconnection pattern, we have several important teleconnection pattern in the Northern Hemisphere. In the Pacific, we have PDO, and then we have ANSO, and North Atlantic, we have NAO, we have AMO. And then in the Arctic, we have Arctic oscillation and Arctic dipole anomaly, or we can call the Central Arctic Index. The time scale have 2 major time scale, decadal time scale and interannual time scales. So this is the data we look at over the from 1850 all the way to 2017. The left column shows the ice extent anomaly. You can see the Beaufort and Chukchi Sea, and then Letop and East Siberian Sea. These 2 are the ice decrease the most, the fast in these 2, which open up the northeast passage. So that is very important. And Barents Sea and Kerat Sea also the same here. And Central Arctic is less, and we can see there's a multi-decadal signal in the ice signal here, anomaly here. So to the right, and we see the Arctic average air temperature. We can see the multi-decadal signal. Blue, cold, red is warm, and then right now we are on the red side. And then we can look at the AO, and recent decade we have a warming, more warming than cooling. DA, the same thing. We have more warming than the cooling. And NAO, the same. And particularly AMO. And you see the decadal, multi-decadal signal. Right now we are still on the warming phase of AMO. How about PDO? PDO, yeah, blue, negative PDO mean warming in the Arctic. And we can see in recent decade have a cooling and warming, and recent is a little bit cooling. So then we do the EOF analysis. The key mode here is mode 1 is in phase sea ice oscillation up and down at the same time. That is due to the thermodynamics, sea level, SAT forcing. PC2 is out of phase oscillation between the Pacific and Atlantic Arctic. That is the dynamic one. You can see the red here, out of phase. This is a negative, this positive, the same thing. Negative, positive, the same thing. We have a 3 periods, the longest one, and then from 84 to 2017, and then 79 to 2017. This is the last 4 decades. They have the same feature. And then if you look at the time series, the mode 1 time series have the multi-decadal signal. And PC2 have strong interannual variability, but still have some of the multi-decadal signal as well. Then we do the regress the PC1 time series and PC2 time series to the sea level pressure and wind, SAT and sea ice concentration. And we found PC1 is mainly zonal anomaly, zonal wind, and produce Arctic-wide pan-Arctic warming and the whole Arctic on the melting. And PC2, we can see the when we have a dipole anomaly here, and we have meridional flow for the wind. And if you look at the SAT, have out of phase in the Pacific Arctic on the warming, and then Atlantic Arctic on the cooling. And the same thing for the sea ice concentration, significant warming in the Pacific Arctic and cooling, and less ice in the more ice in the Atlantic Pacific, because they transport the wind at the back, the Pacific, the ice from Pacific to the Atlantic side. And we do the composite analysis for all these 1, 2, 3, 4, 5 composite analysis, and they come out to be the same. So I don't want to explain here more, but in the recent decade, and this is the case. So we know the ice albedo feedback loop is on the annual basis. And if we have warm SST and melt ice here, and ice have a negative anomaly, less ice will increase the ocean of decrease ice albedo, and then ocean will absorb more heat, and then will have enhanced the warming again on the SST or SAT. So this is the aware or feedback loop. And we know the global warming here, it direct impact the SST and SAT in the Arctic, over the Arctic. And in recent 4 decades, we know the teleconnection pattern also have warming impact, direct impact on there. And we also have a wind director driven the Pacific Arctic ice to the Atlantic ice, Atlantic Arctic. Then these 2 global warming together with teleconnection induce warming. So enhance the Arctic temperature. Are you drinking water? Huh? Hello? Do you hear me?
I think that was an accident.
Okay. And then together Arctic temperature amplification enhance the warming in SST and SAT. Then speed up this ice albedo feedback loop, positive feedback loop. So that is the case in the Arctic. Then based on the funding, and we like to do something more quantitatively, rather than just review the mechanism. Can we use the, can we build a model, can handcast and forecast of the seasonal ice? So idea is, we know teleconnection pattern influence the control the sea level pressure fuel and wind and SAT fuel, and then impact the Arctic September ice. But if we do the forecast like this way, it's too much. And so we like to jump directly from teleconnection pattern to the September ice, because we believe observed Arctic September ice include all the impact from sea level pressure, wind, SAT, and also other local forcing. So we use this method in the Great Lake, and using 4 teleconnection pattern to do the handcast and projection Great Lake ice. So we already done in the Great Lake. So every year we use this statistical model to project the seasonal lake ice. So we just move this to the Arctic. Then this is September ice time series. Because Barents Sea and Barents Sea and Baffin Bay have very low variability, and then we remove it because they are not the random variable anymore. Step 1, how we set up the model. We do the monthly scatter plot on each index. For example, here's an AO index versus ice cover. And then look at the linear regression and then quadratic regression. For example, in the monthly Arctic index for January, February, March, all the way to September. We don't use September because September is the month we want to project the ice. But we put it here to see how good it is. The significant correlation right now is February and July. However, July have a positive correlation with the ice, the AO index. That's wrong, physical wrong. The correct relationship is AO index positive. We have a warming in the Arctic, and they have less ice. So we pick up this one. And each index, we do the same thing. We do the same regression, do the same scatter plot, do the linear regression and quadratic regression to see which month is the best. Then it come out with all the index here, AO, because quadratic and linear, we have a correlation and we have a p-value. So they are even not 95 significant level, but it's considerable, cannot neglect. And DA have only linear, and NO quadratic and linear, both should be considered. And Anino is linear, and MO, both linear and quadratic, we consider. You look at the linear one, MO play the big role here. It's a negative 0.436. It's the highest correlation with the September ice cover. And PDO, we have the same, and we take both linear and quadratic. And consideration is a significance, positive versus negative, which means physical should be correct, and closer to September. And so that we pick. And then the journal equation it's very simple. September ice cover can, I think, is the function of interannual teleconnection indices. And then the interaction between the interannual teleconnection pattern. Then decadal teleconnection indices. And this is a decadal interannual closing interaction. And then decadal interaction, which is a AMO and PTO's interaction. Because of their time scale different, sometimes they are in the same phase, sometimes they are out of phase. So we need to consider their interaction or interference. And in the Arctic, based on that equation, and then we train the model into and to derive the equation. I think every student can do that. Every summer intern can do that if you give them something. Sub here is among 2, okay? AO sub 2 means February. Square means quadratic. And CIA sub 1 means January index. So all these indexes are before September. So if this model can do the handcast, and then we can use the indices, predicted indices before September, and then we can project September ice extent. This is the interaction between the interannual teleconnection pattern. So, and 3 is a decadal, decadal forcing. And this is a decadal and interannual interaction. And this is an interaction between decadal teleconnection pattern. Then we compare with the model and observe time series and this Chukchi, and the correlation is a 0.78. This Siberian is a 0.7. So we miss true value, the model missed the extreme value. So, but the phase more or less is there. Central Arctic is a 0.76, and Barents Sea is a 0.6. It's the lowest. You see, it's the poorest, but even though it's all 95 significant level over. These are entire Arctic and 0.77. So this is a correlation. They're all above the 95 significant level. In conclusion, handcast regression model using monthly index, and we can handcast the September ice cover over 95 significant level. So we use an individual at the beginning, before we train the model, it's a weak correlation, not over 95 significant level for individual correlation. However, we put them together to make it stronger. So because we catch up the significant physics, the dynamic process here, it works best with the largest variability ice record, of course. And we can use this model to do the regression, to do the seasonal projection. That can be done. So I think in the future, we will do it. So thank you very much.
Thanks very much, Jia. If you have questions for Jia, you can raise your hand. I think that's in the under the reactions button, or you can simply unmute and ask your question if you'd like. Just for clarification, Jia, do you submit your forecast to the ARCA Sea Ice Outlook?
No, not yet. So We haven't. I'm writing the manuscript right now, so
Okay.
I really wish I have manpower to do that. I think I will do it. Try to do this year.
Okay. Miyuan Wang, would you like to unmute and ask your question?
Sure.
Hi.
Hi. Nice job, Jia. I do have questions. So look at the time series you did. So you train the time series, use September CS extent. Is that up to 2022, or it seems like you're ending like early 2000 something, right?
Yes. That is when I write the manuscript, I found I asked some why you only train the model up to 20 something.
But actually that's okay, because that's
he said he want to train the model here and then use the later data to test the model.
Yeah, that's exactly my question. Have you tested that part? Because
not yet. So this is and however the other sample interim using the entire record. It's 150 years and 70 years and 40 years record to do the entire regression model. Not for the September, just for the summer.
Right.
For summers. So yes, that is I need to do. Yeah, thank you very much for the good question.
Yeah, because if you simply extend the time series to up to 2022, it's very easy to verify your forecast model is correct or not, and that's kind of really used in the AI currently. Use part of the data to train your model and to verify user entire series. And my other question is, right now you're ending like 2000. If you add 10 more years, are you getting different relationship? Because we all know the sea ice minimum reached 2007, so that's probably changed the a lot of things in the Arctic. We are in kind of in the new Arctic system. So I was thinking if you can extend your training series under 2000, under 2015 or something, just test out, see if you get a similar relation or not.
Yes, thank you very much. This is a very, very good question. And we are going to do the entire period model, train the model using the entire record.
Okay.
And also use the half of the record and test the model in the later half. And then using later half to train the model and test using the first half. But based on my Great Lake paper and research, we found the longer the record to train the model, the better is the model.
That's true.
So we will do that. Yeah, thank you.
Okay, Mike, would you unmute and ask your question, please?
Yeah, I guess I'm curious why you didn't include some measure of the change in global average temperature as directly something to regress against. I mean, it could have been the Northern Hemisphere ocean temperatures, or it could have been something else, but why not include the change in the global average temperature rather than trying to sort of subtract off, I guess, around some sort of linear fits that you do over different periods?
Yeah, this is we don't use the temperature directly. The reason is we want to use the indices only have potential to do the projection. If use we all know the temperature, Arctic temperature and sea ice have a very close, very strong correlation, negative correlation, maybe at negative 0.8 or 0.7. However, you have to predict the global temperature or Arctic temperature first, and then predict the sea ice. But now, because the teleconnection pattern, these are a new idea, right? And teleconnection pattern is the index is very easy. It's pretty easy to be projected by NOAA's I think climate prediction center. And we use this predicted teleconnection pattern, and then we can do the projection. So we just skip away or jump over all these temperature related things. So that is our idea.
I guess I would think you could do it over the, the average temperature over the past 6 months or something like that, and have, or 3 months or something. But it just seems a little strange to have to put in these slopes, because that's going to be a little bit hard to. I mean, those are based on observations, and I guess it's a little strange that how you're going to look ahead and what might happen because you won't know the slopes necessarily. But why not just tie it to the? I mean, I can understand you don't want to have to predict it, but why not just use some running average of recent ocean temperatures or something in the northern hemisphere or the North Atlantic region or something as a metric to automatically take that out, and then the various oscillation and indices would be variations around some sort of large scale change in the mean.
How can you get the water temperature below the ice? There's no way.
I don't mean in the Arctic. I don't mean the water temperature in the Arctic. I mean out of the Arctic.
Okay. So our, for example, North Atlantic AMO represented by the SST anomaly. So actually we use the index, and then actually, so idea is the entire observed sea ice include all the forcing, including SST, Northern Atlantic and Pacific SST anomaly. So we just make it is this is not conventional. It's just I jump over all of this process, like my that I think schematic as diagram. I just jump over. Just our idea is between the traditional conventional statistical model and the data mining, right? Or AI, if we want to say AI.
I just thought NAO and all those others were gradients between two positions rather than the absolute values. And so you want to have something that covers the absolute value of the rising temperature, not just gradients between one place and another place or something, and the pressure or something.
The temperature, Arctic temperature, not only influenced by AMO, all right? Also by other teleconnection patterns. So they are interact over there, very complicated. It's not one index, one pattern dominate the Arctic. It's 6 right now.
I think we'll have to move on in the interest of time. Thanks very much again, Jia, for your presentation.
Thank you.
Our next speaker is Philippe Goulet Coulombe. He's professor in the Department of Economic Sciences at the University of Quebec in Montreal. He is part of the UPenn-UQuam team contributing to the Sea Ice Outlook. So I was intrigued by his economics background and the economics background of the UPenn-UQuam team. And so I'm very happy to have him present his forecasting scheme. His title for his talk today is Econometric Models for Sea Ice Forecasting. Philippe?
Yes, thanks so much. Let me share the slides. That will be. It's coming. Okay, so yes, first of all, thanks so much for inviting me. Really, it's really cool to be here and hear a lot of these good ideas floating around, a lot of statistical stuff, a lot of good discussions. And given that I'm an economist and most of my team members are also economists and statisticians, we still have a lot to learn about climate. So every time I do this, I learn a ton. So What I'm going to talk about today, as the title suggests, are econometric models for sea ice forecasting. So obviously that's the background that we have. And it turns out that a lot of the stuff that econometricians have been thinking about when it comes to forecasting macroeconomic time series can be used and leveraged to model, I think, climate time series. So that's what we're gonna go through today. I mean, yeah, and I say econometric models, but now, as things are, it's sort of hybrid of machine learning and econometric models, but they have like this economic inspiration to them. So I guess just to get started, if you haven't heard about us, obviously we have these forecasts called the UCAM forecast, and we submit them to the SIO. I think we've been doing that for the last 4 years, and we have a suite of models. I'm going to talk about 2 or 3 of them today. And this is like a graph you can find on our website. During the summer season, we basically do daily forecasts of sea ice extent. So we use daily data and we provide forecasts. And this is basically a screenshot of what you can see somewhere at the beginning of September. So you see the path of forecasts, and you also see the confidence bands around them. You have different models, so there are different paths. Sometimes the forecasts in June, they're a bit off, and then they eventually converge to the observed value. And then you have this thing called the Varctic, which is one model we're going to be looking at. This one is a monthly frequency model, so that's why you only have 3 bullets right there. So let's dive right into it. So perhaps first, just to give a sense where all of that stuff is coming from, it's an ensemble of papers that started when I was doing my PhD at Penn with Frank Diebold, and they had a bunch of papers forecasting Arctic sea ice, mainly with quadratic trend models, and there's a few new papers that followed from that. Some of them are already published, some of them are in late stage of revision. And today I'm going to talk mostly about this thing we call the Varctic, which was published in the Journal of Climate, I was about to say last year, or 2 years ago now. And we're going to actually use a macroeconometric model with a bunch of data and see how, in fact, it can help by being a bit of a hybrid statistical dynamical model in its philosophy. And we're also going to talk about paper number 4, which is machine learning based nonlinearities can help for short run forecasting, especially when they are cast within a model of econometric inspiration. So first, model 1, the so-called Varctic, is basically it's called a Bayesian vector autoregression. So vector autoregressions are everywhere in empirical macroeconomics. It's a model that we use we put a bunch of economic series in there: GDP, unemployment, interest rates, and you can go all the way to 20, 30, 40 different variables. And I haven't seen some of them with 120. And you put that in a sort of a dynamic statistical model, and you can look at what we call impulse response functions. So it helps us evaluate how a statistical system responds to different impulses. And basically, it's a model that won Chris Sims the Nobel Prize maybe 10 years ago. It basically changed how we do macroeconomic analysis because it allows for much easier way to disentangle causal effects and things like that. When it comes to climate, obviously the landscape is a bit different. The data is different, and causality is always an issue, but maybe the sources of why we might have a hard time finding it are not the same than when you're dealing with economic agents. Nevertheless, when we thought about that, we realized that perhaps this VAR model, which I'll show you the equations of in an instant, is actually a good compromise between a fully structural and a purely statistical approach. And structural, that's the word, I guess, that economists tend to use when we think about a theory-based model. I think in the climate community, it's more like a dynamical model. That's how we would call it, but that are inspired from theory or from physics, right? Versus statistical model that actually take data points and try to map them onto one another. And what we're going to say with the Vartic is that somehow by the structure of the statistical model, it's not just statistical. In fact, maybe there's more to be said, and maybe we can actually learn something about dynamics, not just correlations, not just trends and things like that. And really, we're going to have a dynamic system, and this VAR, usually the VARs in economics are stationary, so they keep around a steady state. Here, we're going to have a diverging VAR because obviously the Arctic is diverging towards the physical constraint of zero ice, as you well know. And this model is going to help us assess the importance of different variables in amplifying various forcings, as usually we call them feedback loops. So, the way the model works, basically we have this equation here. It's a linear model. So we started with the easiest thing. And the reason why we're doing it in a Bayesian way is that the Bayesian estimation techniques allow for regularization of parameters. So when you have a model with many, many parameters, you want to regularize it so it does not overfit. So Bayesian methods can help when linear models tend to have a lot of parameters. And this one surely does. It's basically a linear multivariate model. We do it on aggregate data. So these are variables aggregated on grid cells above a certain latitude. And we look at sea ice extents, CO2, total cloud covers, sea surface temperature, air temperature, precipitation, sea ice thickness, and sea ice albedo. I'm not going to go through all the details of these things and how they were assembled, but we now have a nice CSV file that people can use to play with this kind of aggregate data. And we call it our VAR 8. So this VAR is going to be using 8 variables. And as you can see, what's nice about this framework, so like I said, and I'm going to show you later how it's useful to do analysis, but also it's kind of easy to add another variable. You just take this vector here, because this is not a single target. This is many different targets. And we're going to all model them jointly with this dynamic system, where it's basically a function of its past values and the past values of all the variables. What's nice here is that I can easily add new variables, especially when I have regularization to guard against overfitting. So if you wanted to include economic indicators in there, which we did not in this first version, I mean, you could also add, if you think we forgot about 2 or 3 variables, you can add them and see how it's going to change the dynamics of this estimated system. So first things first, you can do a long run forecast with this thing. So we took, this is basically the September, well, this is not just a September data. In fact, it's all the data that we deseasonalize. So you could call them a bunch of synthetic Septembers, but they are put on the September level. And we fitted the model on all those monthly observation. So when we did that back in 2019, then we could iterate the VAR forward. It's a dynamic system, so it's complete. And then you can just shuffle it around and let the dynamics do what they do. And since it has what we call an explosive root, the dynamic system is diverging, and it diverges to get us zero Arctic sea ice somewhere around 2016. Then you have the different bands around that date. So the Bayesian approach gives you that straight out of the box. What I think is more interesting is that unlike most statistical models, you can in fact interpret a bit what this model seems to be capturing. So we look at things called shock. So it's basically a deviation, the series, you can call that in fact an anomaly. So it's a deviation of the variable with respect to its prediction based on the other data in the system. And we can document that the CO2 shocks, for instance, have sort of a delayed effect. It takes over 2 years for any anomaly in CO2 to be visible there. But when we look at anomalies in albedo or in air temperature, the impact can be basically in the same month, and then it fades away. So you really see dynamics there. And then that's what's cool about those VAR models. It's a statistical model, but there's some dynamics that you can look at. And in fact, you can even use these things. You can estimate it on model-based data and see how the empirical data has different dynamics than the model-based data. So you could be using these sort of tools. Now, in the interest of time, so that was the first model. I know it went quickly. I just want to give you sort of a bird eye view on all these things. So model 2 and 3, something we call Feller and FEML, and these are much simpler than the previous one. At least the first one is really just a linear regression. And what's the advantage of these things? Is this one is only using daily CI's data. So you can very easily construct forecasts for every month at every horizon. So I can do the forecast 2 months ahead, 3 months ahead, 2 months and 11 days ahead. So really they're quite flexible, rather easy to use and quite malleable. I mean, here we only have 3 regressors. And you might think it's a very simple and simplistic model. Somehow, no, because it's called a feature engineered linear regression, not without reason. It's because the features have been engineered out of the daily data so that even with very, very little data points starting from the 80s, we can in fact have nicely estimated parameter, and we actually capture the key features so to have good forecasts. And I'm going to show you really if they're good or not in a couple of slides. Now the FEML model just takes from there and apply a model called macro random forest, which I designed back in my PhD days. And it was inspired from modeling macro series with machine learning methods. And the idea here is to, I don't know if you ever heard about something called random forest, but in fact any machine learning model could be used. But the idea rather to model the data directly with random forest or any nonlinear, non-parametric machine learning tool, you can in fact model the variation in the parameters of a linear equation. And what's nice about this is that it's much easier to interpret. You can look at the time varying coefficient, and also when you don't have so much data to estimate your model with, and you know that some features have to be important, this is a way, and a pretty good way, to win at the bias and variance trade-off. So like I say in the third bullet point, macro RF is particularly well suited for modeling short time series. It turns out it's a statistical problem that the econometricians have. I think people that want to apply statistics to climate data also have that to some extent. And this new machine learning tool, you have a Python R package, so it's rather easy to use. So like I said, both are easily implementable, provide good forecasts of aggregate CIs all year long and at any horizon. So they're pretty convenient for that. And those forecasts can be computed in obviously something like 2 or 3, I mean, maybe 4 seconds in the case of the second model, and a quarter of a second for the first one. So they're rather pretty easy on that front. So what about performance? So what is this graph? This is root mean squared error of predicting September CIs at different horizons. So when it's minus 120, it's basically 120 days out. So 1st of June. And then this is what we call a glide chart. This is the MSEs of predictions of different models as we approach the target date. And very importantly, these are all out of sample. I think we talked earlier about train and test and testing the model. All the models that we do, they are estimated up until, say, 2011, and then we forecast 2012, and then, we move somehow recursively, and we do that every year. So when we do the forecast for 2013, the data that we use is up to 2012, and we just move like that, which obviously avoid any form of overfitting, and you also avoid any form of look-ahead bias, which is extremely important. So these RMSEs, RMSEs are good estimates, in fact, very close to what you get if you just submit in real time to the SIO, which is important for proper evaluation. So first of all, we have the Feller, which is the purple line. So that's this small, simple linear model. And then we have a refinement of our FEML model, which is the red line. And then the median of the SIO, which is usually a good benchmark, sometimes quite hard to beat. It's just the wisdom of crowds, right? We have hit there with the green bullets. And what we can see, it depends on the horizon. For early horizons, the best model we have seems to be Feller, up until approximately maybe the beginning of July. And then from July until maybe beginning of August, the pocket FEML, has a very, very strong advantage against all the linear models. So there seems to be some nonlinear things that the machine learning models is capturing that's very helpful here. And as you would expect, the RMSEs, as we approach and glide into the target date, obviously, if we're forecasting September and we have observed 20 days out of September already, the RMSEs are shrinking, and that's what we see here. So all these models, we use them. We provide forecasts during those 4 months, and we know at which point during the summer part of the cycle, which model is best to use. And that's what we actually do when we submit to the SIO. We look at this plot, say, okay, and now we're in July, so yes, use pocket femal. When we're in June, we're using the feller. And sometimes we submit also the Vartic separately. And, to complete and not to, blow up too much the time limit, this is a graph from the femal paper. And we see, this is September Arctic sea ice. And these are forecasts that we made using feller and femal at different points in time. And in July, where we really see that femal as an edge, we really see that, especially around after big shocks downward, big downward anomalies, we really see that it picks it up much better than the plain linear model. Really, it's actually close to the forecast you would make almost a month later. So we really see that nonlinearity seems to help when a big downward anomaly has happened in the years prior. So that at least what we've seen. And we also see that the machine learning method, the red line, was much closer to the 2012 anomaly than the linear one. And this is important. This is completely out of sample, because if it was in sample, you could believe that the machine learning method is just overfitting this particular data point. But this was actually a forecast made using data back in 2011. So yeah, I'm just going to conclude by saying we look forward to the next summer. All those models are available to this sort of interactive interface where you can see the forecast throughout the season. You have different variants of our models, and we also compare it to previous year and then to obviously what we expect this year to be about. So yeah, I think that that's about it. Thanks for your attention.
Thanks very much, Philippe. I think I should get this out there right now while I have a chance. So in your variable list of interest, you had the Merit2 albedo, which is Merit2 sea ice albedo is a climatology, and then the other thing that goes into that, of course, is the sea ice fraction. So is it important to look at the input variables for orthogonality or independence? Is that important in your application?
Well, in the Vartic, which is where we use this albedo thing,
Right.
the model, the way it's doing this shock analysis, it's first by orthogonalizing with respect to all previous available data, so the lags. And also, when we look at the shocks, they're all orthogonal. So there are, obviously, when we look at the shocks of albedo, it's orthogonal to the shock that's already in Arctic sea ice. So indeed, there we look for that. But that's indeed a limitation that this albedo data is in part from model-based data, and we're aware of that. So it's obviously doesn't make things easier.
Okay. Are there any questions for Philippe? I see Wisla has his hand raised. Wisla, can you unmute and ask your question?
Can you hear me?
Yes.
I have a follow-up to Richard's question. Using multiple data sets, observed reanalysis and model output to train your models for AI type approach. Are you concerned, and is there any issues that you see with those data, multiple different sources being inconsistent with each other?
So, yeah, that's a super good question. So when it comes to causal analysis, you certainly have to be more careful. When it comes to forecasting, and we use them in the pocket femal and things like that, I think obviously it doesn't help, because you can think about plain what we call attenuation bias. If the data is full of noise, eventually the model is just gonna not use it because it's useless. But you can think the machine learning methods sometimes help in that regard. It can take data that's hard to use and make it basically through the implicit feature engineering, make it work a bit better. When you do causal analysis, however, you have to be a bit more careful because interpretation might change. But another thing I think we also have to be careful with, and we're very careful with that in the paper, is when the data is available. So when we forecast using a lot of this heterogeneous data sets, we really make sure that when we do, say, a forecast in July for September, we make sure that whenever, if it's July 14, then that data was actually out there and available on July 14 of that year. And some series, my knowledge, I think they might take 2 or 3 months to appear. So we call that publication delay. So we really take care of that. So yeah, no, a lot of data stuff to think about.
Thank you.
And Jia, you have your hand raised.
Well, it must be a very
Jia?
deep question.
Are you there? We can't hear you.
Sorry.
Okay.
So Hailong's question in the chat, and so can you repeat the question, Hailong?
Well, let's just see if we have any more questions for Philippe first. So Philippe, with an AI system, you have, of course, the training period and then the application. I guess this is similar to the question that was posed to Jia. Do you feel that you have, is the training period sufficient for what has been characterized as the new Arctic, where relations can change rapidly? Can you comment on that?
Yeah, sure. I mean, obviously, if the Arctic changed completely from one day to the next, and you use data, then you can be in a bit of trouble. But I think the methods and nonlinear methods and the way we use them through time varying parameters and things like that, it's usually can capture structural change. Obviously, if it's unforeseen structural change, make things harder. But usually that can help, and there's always the question of the historical record that we have, right? We're training these models starting from the 80s, so there's always also this question of are we capturing correctly some more long run phenomenon using that data? You really have to think about that. But to my experience, when we train those models using data going further back, often from model outputs, but nevertheless useful stuff, it didn't really change the conclusions that we had about long-run forecasts and things like that. But surely plain linear models are subject to the dangers of structural change. Machine learning models a bit less, but they're not completely immune to it either.
Yeah. All right. So, it's just past the top of the hour. If anyone online needs to go to another meeting, I think we can go to Hailong's question for Jia. Hailong, and if you're still there, could you unmute and ask your question?
Yeah. So I was wondering. So when I look at the monthly regression results, they differ quite a bit, right, from month to month. I was wondering if that's due to those smaller timescales, much smaller timescales. So I wonder how, in your regression model, how those small timescale processes are considered.
So the concept of my model is very simple. So the observed September ice minimum includes all the forcing, including shorter timescale, longer teleconnection pattern. So everything are in here. So that means the data record all the forcing, memorize all the forcing in my record, right? So now we use a teleconnection pattern indices only. That make it things easier, much easier. I don't want to involve all the temperature, all the albedo, everything. I just, because the climate index is easy to get, really easy to get. You just go to website, you put in the teleconnection pattern indices, just plug into the model, and then just 1 second you get the result.
Yeah, I totally understand. I'm just, my concern was similar to Mike's. So sometimes if we want to get the more accurate forecast or prediction, those processes probably would dominate. I might be wrong, right? But those.
Oh, no, you're right. I think we can do the iterative input of the SAT, surface air temperature, accumulate degree freezing day, for example. So every week you update the model using the freezing degree day. That's in the Great Lake, we do that. We accumulate all the temperature and then update the model every week or every 2 weeks. Okay. So in the Arctic, we can do so. But this is just give the very, I think the big picture, I think, but the correlation is so high.
Okay, I
amazing,
see.
amazing.
You have a bias correction process at much smaller time scale. Okay, I probably missed that. Okay,
right. This is a longer time, but your process, we can use the iterative addition of the surface air temperature, or if you have I think SST, that would be better. So
okay,
that can be solved.
Thank you.
You're welcome.
Okay, are there any other questions? Ed, we can get to your question now. Go ahead.
Thanks, Richard. Hi, this is a question for Jia. Thanks for your presentation. And I just wanted to, I don't know if I misheard you, but I think in your slide 15, you said that the correlations in February and July were significant, but the p-values were 0.2, like they were not significant. And I'm very surprised that when you do the multiple variable model, that you get really high correlations above 0.7, right? So you explain
yes.
in 50%.
In summer.
You explain in 50% of the variability of your time series, but then if you look at the individual predictors, I think only August, the AMO in August had a correlation that was around 0.4, right? So that's 16% of your explained variability. All the other correlations were like below 0.2. So you explain less, you're playing 2 or 3%. And I don't know if that adds up. And then my other question is, are you building are you using the leave one out method for those reconstructions? So when you're predicting 1977, are you building your model with all the years apart from 1977? Because if you're just building a single model for all the years and then predicting the years, that's not independent, right? You're using the year you're predicting in the model you're building to forecast that year.
Yes, you're right. Very good question. All the indices in climate, they say, oh, they are independent. They are not independent. They are intercorrelated.
But that makes it even worse, right? Because if you're in multiple linear regressions, if your variables are not independent, that makes it even worse than if you do have independent variables.
For example, ENSO and PTO not independent. NAO and AMO is not independent. However, people use it. Then what we do, we have an interference. We have an interaction term that will cancel all this concern. That will remove all the concern because they have an interference interaction term, right? They have a phase difference.
Okay, but do you use, regarding my second question, do you use a single model for all your years, or are you using the leave one out method?
We use a single for all the year.
Okay, but I don't think you can do that. I don't think you can justify doing that.
How come?
because you're do you understand? Because you're building a model with with data that then you're forecasting. They're not independent, right?
What is not independent?
Your forecast to the model you're using. It's you're feeding in the answer into the model. Is like the second talk was quite careful about using independent data, right? So building a model with data to 2011 to forecast 2012. You can't use data of 2012 to then forecast 2012 because you're baking it into the answer, and your values are going to be artificially high. And
So,
I would recommend, for example, use the first half of your period, build your model, and then forecast your second half.
Yeah, this is what we are going to do.
At the very least, use the leave 1 year out. You can't,
we are going to
otherwise,
do. We are going to do.
it's not a true forecast.
We are going to do 3 experiments. One is using the entire time period to construct a model and do the projection, hindcast. Another is use the half of the first half of the data to train the model to predict the second half. Then use the third is use the second half the data to train the model to predict the first half.
Right, but I think from the very beginning you have to do the leave 1 out method.
What method?
Leave 1 out. It's when you leave the year that you're forecasting out of your training data. So you basically have to rebuild your model for every year, leaving that year out. So when you forecast 1950 or when you reconstruct 1950, you use 1951 to the end of your time series. When you forecast in 1951, you use 1950 and 1952 onwards, right? So you're leaving the year that you're reconstructing, you're leaving out of your model, because otherwise you're overfitting it and you're baking in the answer to your model. And it does make a difference when you're building short time series.
Thank you for this suggestion. If you have a paper or report, send me.
I mean, I
send
think
me a copy, and then I can learn it.
Like in statistical,
okay, send me that.
Well, I think it's just good practice in statistical modeling. So I think any on statistical modeling, you can. It's called. I mean, I think other people might use other terms for it, but I've seen it called the leave 1 out method, right? So you're not using the year you're forecasting or reconstructing. You're not using that in the statistics that you're building in the model you're building.
Oh, that can be done. That can be done. Yeah.
But regarding the first question, I know you highlighted February and July in your slide 15, and I remember looking at those scatter plots, and
right.
I didn't. To me, they were not significant, and the p-values were 0.2. So that's.
I know, that is surprising to me too. We in the Goulet, we did the same. At the beginning, the correlation only 0.1, 0.2.
Right.
It's not significant.
No.
However, we put together, we make it so significant. This is
that's where I get suspicious. That's where I get suspicious. That there's overfitting. And the other thing is that there is quite a bit of literature showing that the relationships between the teleconnection patterns and Arctic sea ice, they're not robust. They change in time. Like if you look at the relationship between the NAO and sea ice between 1960 and 1990, and then between 1990 and 2010, there's a lot of variability in that relationship.
I agree that. So this is why we will do the half and half, or maybe in the recent year, we just use recent years the later half model to do the projection, to do the hindcast.
Yeah, I strongly recommend doing that.
Right, we can do that. Because the model is simple, the simpler the better. This from physics point of view. So.
All right. Thanks for your question, Ed. I'd like to thank my speakers, presenters today, Jia and Philippe. Thanks so much for presenting at our modeling meeting today. For next month, which is April, we'll have a meeting on polar amplification. And so we'll see you then. Thanks again for everyone who participated, for everyone who asked a question, and thanks, and we'll see you in April then. Thanks very much.
Okay, thank you for Edward for the question. So. Mhm.